Welcome back, folks. We're going to look at doing nodal analysis very quickly. I'll admit I don't use this shortcut as much, but it's just as good as mesh, and we can go right to the matrix form and solve it. I've been practicing it over the past few years as I've started to teach this, and it is pretty useful in analyzing a circuit quickly, certainly while we're in class, when what we want to do is not focus on the analysis. We got to get you good enough that you can do the analysis without too much thought, so that we can start talking about theorems, and we can start looking at phasor analysis and transient analysis, all that good stuff. The analysis part is just the first building block that we use to go do all of those other things. So it's super important. Okay, so to learn the shortcut, we're going to go back and we're going to look at all of the circuits we've already done, but we're going to try to do them quickly. So the very first circuit we looked at was this one. And now we want to go right to matrix form with this circuit. Okay, so we're going to label our non-reference nodes, and we're going to make a plan. Okay, so I see 3 non-reference nodes, and I'm going to do it down here, I think, just because I have a little more room. Okay, I'm going to invert that, and I'm going to have some right-hand side to it. Okay, so they're all going to be KCLs for these first few problems, right? So I'm going to write the KCL for A, the KCL for B, and the KCL for C. Okay, so the way I do this is I look at node A. I'm writing a KCL for A, and I say, what is connected to node A? What resistors are connected to node A? And I see that this 2 ohm is over here, so it's going to be positive 1/2. Okay, I'm writing the KCL for A, so when I move to the B column, I say what is connected to A that's also connected to B. Okay, and it's also this 2 ohm, but it's on the other side, right? I'm writing it for A, but I'm working in the B column, so it's going to be negative. So I get negative 1/2. And then what's connected to A that's also connected to C? Nothing. Okay, and then the right hand side is for any constants. So here I have 6 amps, and since it's going in, I'm going to call that positive 6. First one's done. All right, with a little repetition, I'm hoping you can ask yourself these same questions as you're filling out the matrix form. Okay, let's do it for the B node. So we're going to write a KCL for B, but we're going to start in the A column. I can write those here, right? These correspond to the order of the unknowns that are going to pop out of this calculation. So what's connected to B that's also connected to A? And it's this 2 ohm again, so it's going to be negative 1/2 over here. What's connected to B? We got the 2, the 4, and the 4, right? So this one's going to be 1/2 plus 1/4 plus 1/4. Okay? Don't be sloppy and think that you can do 1 over 2 plus 4 plus 4. I've seen very good students make that mistake because they're moving quickly and they're not thinking about just how, like basic fractions that you should have learned a long time ago. I bet you all learned it. I know you all know it. Don't be sloppy, okay? So don't do that. That's bad. I'm not even going to leave it on the pad. I don't want you to think that it's correct. Okay, so what's connected to B? Since that's the one we're writing for, it's all positive, and we add them all together. What's connected to B that's also connected to C? And I see this 4, so it's going to be negative 1/4. And then there are no current supplies connected to it, so it's 0 on the right-hand side. Last one. What's connected to C that's also connected to A? That's 0. What's connected to C that's also connected to B? The 4, so we get negative 1/4. And then what's connected to C? And I get positive 1/4 from R3 and positive 1/2 from R4. There are no current supplies connected, so that's 0. Okay, so that looks pretty good. This looks like it's 1, right? So let's pick a different color. If I reduce that, that's going to be 1. If I reduce this, it's going to be 3/4. Okay, and hopefully with any luck that's going to be equivalent to our previous problems. I'm going to pause it while I dig that up. I didn't have it at my fingertips, so hold on tight. Okay, so from our previous video, I'll write that in a moment here, our solution looked like this. Clean up the little things that were around it when I cut and paste it. Okay, this is from a previous video. Doing it out the long way, which is always good to know how to do it the long way, because that's how you know you're getting it right. But the shortcut can make you fast. You can impress your friends. I would usually say, like, go to Tumors and show off, but nobody can do that right now. So we're stuck doing this. Excuse me. All right, so it looks like we have an equivalent system. I apparently flipped some rows here, but we have -1/2, 1/2, 0, and -6. And that's equivalent to the top row. Everything's multiplied by -1. So we're okay with that. Let's see, we have -1/2, 1, -1/4, and 0. That looks like it's equivalent to the top row. Again, just every sign is changed. That's okay. 0, 1/4, and -3/4. So it looks like those bottom rows are equivalent. So just for fun, my kind of fun, not your kind of fun, although I kind of hope it's your kind of fun. You chose to study this. So did I. So no judgment from me on that one. Okay, 0.5, -0.5, 0, and 6. -0.5, we should always just check it, right? Make sure that we not only have equivalent equations, but we get the identical result. -0.25 and 3/4. And holy cow, math works again. 26.4 volts, 14.4 volts, and 4.8 volts. Okay, go compare the length of this video to the length of that video, and I think you'll agree that the shortcut's pretty useful, and we can get to the same set of node voltages. If we get to the same set of node voltages, we can go find whatever value we want in the circuit. Okay, we're going to go through the rest of these. That's how we get good, right? So stay tuned and good luck.